Okay, hi everyone. I guess good number of us are already here, so we'll start with the session. So today we are going to begin with the idea of current electricity. Now some of you might be thinking, why is it that we are starting with the chapter 2 and not the first chapter? Because as such, right, the first topic of electrostatics and current electricity, they have very a little in common, like the idea of how charges will move and how we will correlate the energy when the charges are made to move. So these are the two ideas on which these two chapters are linked. Otherwise they both are totally different. So we'll start with this, and even the first chapter, right, the video lectures are already available in our concept digital portal, so you can probably take a look at them over the weekend, and if you have any queries in that, we can discuss upon that. So current electricity is an important chapter, guys. Hi Prajwal. Yeah, so it's an important topic not only for the CBSE or the state board examination point of view, but also for the competitive examinations. And if you look at NEET, we do get definitely 2 questions from this chapter. Even in JEE mains or advanced, right, typically it will be a part of this the core topics, electrodynamics. So we do get a lot of weightage for this part in JEE advanced. Okay, so we'll start with the session, guys. So as such, right, for this session we don't really need to have Suhail. Okay, hi. So we don't need to really have any prerequisites for this session, except the idea that how charges will be moving and how do we calculate the energy changes when the charges are moving. Okay, so we'll start with the session, guys. So current electricity topic, right, we are going to be broadly looking at these things. So these are the 3 main areas that we'll be covering in this chapter. One is the circuit analysis. So this is what if we have the combination of resistors and cells. So how we are going to study the combination of cells and resistors is what we'll be covering in the circuit analysis. This is one. And the second part of it is the micro study in terms of how this current or electricity will get generated. Especially we'll be talking about the metals. That's why we'll call it as what? The metallic conductors. In fact, I will have one more chapter, which is the last chapter. There we'll talk about the semiconductors. Okay, so the other part of this chapter is about measuring instruments. So in terms of the electrical circuits, we have some measuring instruments, like we'll have potentiometer, and we have ammeter and voltmeter. So these are the 3 measuring devices that we will be covering. And we also have one more device called as meter bridge. So these are the measuring instruments that we will be covering in this chapter. So this is the coverage of the chapter in terms of what we are going to see. So we are going to be looking at the circuit analysis, which is the major part of the chapter. Then we look at some micro level analysis, which is going to be mostly theoretical. So we'll get questions based on theoretical analysis in this part. And of course we'll talk about the measuring instrument. So what are the measuring instrument that we are going to study? We'll study about the potentiometer, ammeter, voltmeter, and then meter bridge. Okay, guys, we'll start with the session. First, if you look at the concept of how the charges are going to be moving, because in the entire current electricity here we are going to be talking about the movement of charges, and we'll see that the movement of charge is what we are going to be linking to the definition of electric current. Okay, so why charges would move? So this is where we need to bring our understanding from the first chapter, which is the electrostatics. If you have a charged particle, let us say we have a charged particle Q. Now the thing is the Q can be positive, Q can be negative. Depending upon this charge value, right, we will see that if we have an electric field in this region, wherever the charge is present, if we have an electric field, what happens is there is going to be a force acting on the charged particle. and we will study in the first chapter electrostatics that the force acting on the Laurel. Okay, so you are here, fine. So the force acting on the charged particle is going to be what? Q times the electric field in the place. So force acting on the charged particle will be what, guys? The charge of the particle times the electric field in that particular place. So if the Q is positive, means we will see that the force acting on the charge will be in the same direction as the electric field vector. If Q is negative, means the force acting on the charged particle will be in opposite direction to the electric field. So as a result, what we see is positive charges, right, they are going to move in the direction of the electric field. Negative charges are going to move in the opposite direction. So simply saying, right, why we see the movement of charges happening? Why do we have movement of charges? Movement of charges is there. Shanmugam, okay, Kavya, fine, yeah. So welcome, guys. So why charges would be moving? Charges would move because of the electric field. Positive charges will be moving in the direction of the electric field. Negative charges will be moving in the opposite direction to the electric field. The same movement of charges, right, can be also understood in terms of the potential concept. So the same movement of charge can be also understood in terms of the potential concept. Here we will be talking about the energy. So if you look at the positive charges, right, positive charges will be moving from the high potential place to a place where we have low potential. So if we are moving in the direction of electric field, you know what is going to happen? We'll move from essentially high potential place to low potential place. So the positive charges are going to move in what direction, guys? They are going to move from high potential to low potential. And the negative charges, right, they are going to be moving from low potential to high potential. How the negative charges are going to move? The negative charges are going to move from where to where, guys? They will move from low potential to high potential. So what we see is the direction of movement of the charges, right? Tajuddin, hi. So the direction of movement of charges will be what? Exactly opposite. If positive charges are moving in one direction, means negative charges are going to be moving exactly in the opposite direction. So the movement of charges, the reason for movement of charges can be understood either by using the concept of field or by using the concept of potential. Clear, guys? So this is what is Mahima, hi. So this is what is the reason for the movement of charges. Now why are we discussing about the movement of charges? Because the definition of current, right, is linked to the movement of charges. How it is linked to the movement of charges? Say for example, if we take a conductor and we are marking some cross section, let us say we are marking some cross section of the conductor. This is a conductor where we see that there is a charge that is going across this area. So we are marking one area and we are looking at how much charge is flowing through this area. Okay. So if you look at the definition of current, which is something that we are already aware of in 10th standard also, we study about the definition of electric current. It is not something new, but over here we are going to learn a little bit more detail about the idea of this electric current. So how are we going to define electric current? Shashank, hi. So how are we going to define electric current? So electric current is defined as the charge flowing through that particular cross section area divided by the time taken. Say for example, if we take that conductor and let us say delta Q. So either we can use this as symbol for delta or this as the symbol for delta, guys. Okay. If there is a charge delta Q that is flowing through the cross section area A that we are marking over there. So current is always linked to the area of cross section. Remember, guys, this point we'll again talk about it. Current will be always linked to what? Area of cross section. Okay. So if we have delta Q charge that is flowing through a cross section area A in the time delta T, then the average electric current through the conductor is given by what? Average current value will be given by what, guys? Delta Q by delta T. How are we going to measure the current value? Delta Q by delta T. Okay. And if we want to find at an instant of time, then we have in mathematics, right, there is one concept called as limiting concept. So what is this limiting concept? So delta Q by delta T is giving us what? It is giving us the average current. So what we do is we will take In mathematics you will study about this limit the delta t value tending to 0. We will make the time to be very close to 0, and that is what mathematically we will be expressing it as what, dq by dt. So this idea, right, we see in +1 mechanics also, like, you know, if you want to talk about instantaneous velocity, how do you say instantaneous velocity? It is ds by dt, the rate of change of displacement at an instant of time. Clear, guys? So this is how we are going to be defining the electric current. And electric current, right, is a scalar quantity, because here we see that electric current, we are talking about direction, like, you know, it is charge is going like this, but the electric current will not satisfy vector law of addition. So what is vector law of addition? If we have any physical quantity, magnitude and direction, they are required for a vector, but not only these two, the quantity must also satisfy what? The vector law of addition. What is vector law of addition? If we have two physical quantities, right, like say for example there are two quantities A and B, the resultant of them will depend upon the angle between the two. That is what we will see in the vector law of addition. Like the resultant will be given by what? Root of a square plus b square plus 2ab cos theta. The electric current does not satisfy that. Why? We will see once we go into the details of the chapter, but I'll just give you a broad idea. If we have two wires coming like this and third wire is going away, there is a 2 ampere current coming like this, 3 ampere coming like this. You know, the branch into which the current is going out, right, will be always 5 amperes. Whatever is the angle you keep here, the current will be going is always going to be what? 5 amperes. So electric current does not satisfy the vector law of addition. That is why it is not a vector quantity. What is it, guys? It is an scalar quantity. Clear? Now if we look at electric current, what is the SI unit of electric current? SI unit of electric current is what, guys? Ampere. And we use symbol capital A for the SI unit. And this is a fundamental physical quantity. We use either I or A as the dimensional symbol for the electric current. What is the dimensional symbol for the electric current, guys? I or A. In some textbooks we will use I, in some books we will be using what? A. So this is what we have as the definition of electric current. Okay, so we'll move on to the next idea, guys. We have a question. Let's see if we can answer this question. Check this question, guys. I'll just read out the question, and you know, probably whatever the answer you're getting for this question, right, you can type it over in the chat box. Okay, I'll be able to verify that. Look at this question, guys. A charge of 5, what is this symbol? What is the symbol, guys? This is symbol for what? Micro. A charge of 5 microamperes. I think it should be the current. Okay, what is this, guys? It's not charge. What is it? It's current. A current of 5 microamperes flows through a conductor for 30 minutes. For how much time the current is flowing through the conductor, guys? It is flowing for 30 minutes. Find the total charge moving across the conductor. What we need to find, guys? We need to find what is the total charge moving across the conductor. Let's see, you know, if we can get the answer for this, guys. It's a straight question, right? What is it? It is based upon the formula of electric current. So we are given the current, we know the time, we have to find what? Charge. So what is the formula for the average current, guys? What is the formula for the average current? Average current formula is what, guys? Average current I is equal to what? Delta Q by delta T. The charge that is flowing divided by the time taken. Correct. So we need to find what is this? Delta Q value. If current is in SI unit, time is in SI unit, right? Then the charge is going to be coming in which unit, guys? Charge is also going to be coming in the SI system. Okay. So check this, guys. We need to find what? Delta Q we have to find. So what is delta Q value, guys? It will be what? I into delta T. What is the delta Q value going to be? I into delta T. Check, guys. Anyone is able to get the answer for this? You can just type the answers in the chat box, guys. Here the only thing is what? We need to convert the time. Check it. No, time is not given in the SI system. Time is given as what? Time is given in minutes. So we must convert this into what? Seconds. We must convert the time into what, guys? Seconds. What are the answers, guys? Straight question, right? What is it? I guess some of us are able to get the answer. So delta Q will be equal to what? I. 5 microamperes means what? 5 into 10 power minus 6 amperes into time is 30 minutes, right? Means 30 into 60 seconds. We should convert this into seconds. Ampere into second is going to give us what, guys? Coulombs. Ampere into second is going to give us what? Coulombs. Okay. So we have to simplify this. What is the answer, guys? So 30 into 60 is what? It will be 1800. Okay. 5 into 18 is what, guys? 90. So what we will be having is 9000 into 10 power minus 6 coulombs. Otherwise what we can write? 9 into 10 power minus 3 coulombs, which is going to be what, guys? 9 millicoulombs. What is the answer for this, guys? 9 millicoulombs. Clear? Clear, guys? We are able to get the answer for this. Okay. So if all of us are able to get the answer, means we will go on to the next question. Okay. So I guess we are able to get the answer, most of us. We will go to the next question, guys. But before that, right, we have one more idea that we will discuss. So if you talk about the idea of the charge carriers, we said what is the definition of current? What is the definition of current, guys? Yes. Okay. What is the definition of current? Current is what? The rate of flow of charge. In terms of the metallic conductors, right? Because in electrical conductivity, we'll have basically two types of conductors we'll talk about. One is the metallic conductors. Second is in chemistry you will be studying about it. It's called as what? Electrolytes. Okay. So in metallic conductors, which is basically we can put all these metals and semiconductors, everything into this category, right? If you look at what are the charge carriers, the charge carriers are basically going to be electrons. What are the charge carriers in metallic conductors, guys? Electrons. So when an external potential difference is applied across a metallic conductor, right, then what we see is there is going to be electric field set up within the conductor. So if you are applying some potential difference means across that metallic conductor, so we take a conductor and across this we are applying some potential difference, delta V we apply. Then we will be setting up what? Basically we will be setting up an electric field inside. And the electric field that we are setting up, right, will create force on the electrons. Since electrons are what, guys? Negative charges, right? What will be the direction of force acting on these electrons? It will be in the opposite direction to, it will be in what, guys? It will be in opposite direction to the electric field. And this force is what is going to cause the drift of electrons or the movement of electrons. So we'll study about how the drift is going to happen in detail when we talk about the micro analysis. We said, right, in this chapter we are also going to talk about the micro analysis. But broadly speaking, right, what is the reason for the current in metallic conductors? It is the movement of electrons. So what are the charge carriers, guys? The charge carriers are basically what? Electrons. And what is the charge of each electron? I mean, we know that it is going to be what? Negative. But what is the value of charge on each electron, guys? It is the basic charge. What is the basic charge? 1.6 in 10 power minus 19 coulombs. Clear, guys? So what are the charge carriers in metallic conductors? They are basically electrons. Let's look at this question. Here also it is not charge, it is basically what? Current. Look at this question, guys. A current of 1.6 milliamperes. Small m represents what, guys? Milliamperes. What is the question, guys? A current of 1.6, we are in the illustration number 2. Okay. A current of 1.6 milliamperes flows through a conductor for 15 minutes. For how much time it is flowing through the conductor, guys? It is flowing through the conductor for 15 minutes. Okay. Find the total number of electrons moving across the conductor. What we need to find, guys? We need to find what is the total number of electrons that are moving through the conductor. Let's see, guys, who can get the answer for this. So what we need to find in this question? We need to find what is the total number of electrons moving across the conductor. So here also what is going to happen, if you look at the current and time is given to us. So by multiplying the average current with time, right, what we are going to get? We are going to get the charge value, how much charge is moving. And we talk about a concept called as what? Charge quantization. What is the concept, guys? Charge quantization. If this much charge is moving because of electrons, right, let us say this charge we are calculating as what? Delta Q. It is coming because of n number of electrons. Then what we will do? The delta Q is equal to what? N into E. E is what? Basic charge. What is the basic charge value? 1.16 10 power minus 19 coulombs. So first we will calculate what, guys? First we will calculate the delta Q. And then we will use which formula? Delta Q is equal to N into E. Using that we can find the value of N. What is N here going to be, guys? It is the total number of electrons moving across the conductor. Let's see who can get the answer for this question, guys. Second question. Yes, guys. Any answers? So how do we proceed with this? Same method, right? First what we are going to find? We are going to find the delta Q value. What is the delta Q value going to be? The average current, 1.16 10 power minus 3 amperes into time. What is the time here, guys? 15 minutes. We should convert this into the SI unit, right? 15 into 60 seconds. Okay, that is going to give the charge in what? Coulombs. So what is it, guys? I mean, we don't need to simplify it. We can just keep it as it is. We will do the final step. Now what we are saying, this delta Q is equal to what? N into basic charge. What is the basic charge, guys? 1.16 10 power minus 19 coulombs. Okay. From here we have to find the N value. So what is the value of N, guys? 1.16 10 power minus 3 into 15 into 60 divided by 1.6 into 10 power minus 19. Just this 1.6 in 10 power minus 19 will go to the other side into the denominator. 1.6 is cancelled. Then what else is there, guys? 10 power minus 19 will go to the numerator. It will become what? 10 power plus 19. So 10 power plus 19 into 10 power minus 3 is what? 10 power 16. This is what? 15 into 60 is what, guys? 15 into 60 is what? It will be 900. So what we can say? 9 into 10 power 18. What is it, guys? 9 into 10 power 18. So these many number of electrons must be flowing through the conductor. Clear, guys? Check, we must have got the answer as what, guys? 9 into 10 power 18 must have been the answer. Okay. We'll go to the next question, guys. Look at this. This is a sort of reasoning question. A steady current passes through a cylindrical conductor. What is it, guys? There is a steady current that is passing through the cylindrical conductor. Is there an electric field inside the conductor? Because in the electrostatics chapter, right? In the electrostatics chapter, we keep saying that if we have a conductor, inside the conductor electric field is zero. This is a concept that we will be learning in the electrostatics chapter. But when the charge flow is stopped. So when inside the conductor the electric field is going to be zero, guys, when the charge flow is stopped. But if there is a steady current, means what? There is an charge flow, then there will be an electric field inside the conductor. So when there is a current, means whenever there is a current through the conductor, right, inside the conductor there is going to be electric field. When inside the conductor the electric field is going to be zero, guys, because this is a thing that we will be learning in the electrostatics. I'm sure some of us are able to recall that, because inside the conductor electric field will be zero only when we talk about the situation where the charge flow is stopped. But if we talk about a current, right, as long as there is current inside the conductor, the electric field will be what? It will be non-zero, or it will be having some value. In fact, the electric field is what will drive the basically drive the flow of the electrons. Clear, guys? So this is, what is the understanding of the current in case of the metals, and even the semiconductors. Of course, we will see that there is going to be some difference in terms of how the metals will conduct and how the semiconductors will conduct, but broadly for both of them, right, we can think about this is the manner in which the flow of current will happen. Clear, guys? Now we come to another important concept, which is the idea of what is a conventional current. So we said if we apply potential difference, so we have a conductor, we have to apply a potential difference. Means what? One side we must have a high potential, other side we must have what? Low potential. So the device that creates this, the potential difference, right, is basically what we will be calling as a cell, or a combination of cells will be called as a battery. So we'll learn more about cell or battery in this chapter, but a cell or battery is going to be the one that is going to provide us with the potential difference. So the cell will have two electrodes, one is positive, one is negative. So positive side will be the high potential and negative side will be what? Low potential. But what we are observing is inside the metal, right, what are the actual charge carriers? The actual charge carriers are what? Electrons, because only electrons can move. What can move, guys? Only electrons can be moving. So what we see is from this low potential side, the electrons are going to move. The electrons are going to move and they will be coming to the high potential. So electrons are going to move from the low potential side, the negative side of the cell or battery, and they will come to the positive side. But the conventional current idea, right, it always assumes that the current is due to the movement of the positive charges. I mean, this is a convention that is being considered, and of course this is the convention that we are following even today. But we know that the current is actually because of what? In metals, the current is because of movement of electrons. But how do we define the conventional current then? Because conventional current, we are saying it is assumed because of movement of positive charges. What is the actual current we see? The actual current is because of the movement of electrons inside the metals. To help us understand the relation between them, right, let's just look at this case. Let's say we have 40 coulombs charge and minus 40 coulombs charge. I'll just know this is a place 1 and place 2. Now what I'm saying is, try and bring minus 10 coulombs charge from here to here. Try and bring minus 10 coulomb charge from where we are bringing from right side to the left side. Okay, then what will be the final charge values? Just look at it. Minus 10 is coming here, so 40 minus 10 is going to be what? 30. Since minus 40 we have taken minus 10, means remaining is going to be what? Minus 30 will be remaining. Clear? So when I move minus 10 from the right side to left side, that final charge values are going to be what? 30 and minus 30. Now let us look at the other situation. The other situation I am saying is, let us move 10 coulomb charge from the place 1 to place 2, which means we are moving from left side to right side. If you move a 10 coulomb from here to there, right, we are moving from 40, we are taking 10 out, means remaining is what? 30. If we take the 10 coulomb that side, means to minus 40 we add 10, it is going to become what? Minus 30. So you understood what I am trying to communicate. So what I am trying to say is, if we look at the movement of negative charge, let's say we are talking about what? Minus 10 coulombs, which is moving from where? Right side to left side. The movement of negative charge is the outcome. What is the final outcome? Both places the charge values are becoming what? 30 and minus 30. The final outcome is same as an equal amount of positive charge moving in the opposite direction. So clear, guys? A movement of negative charge, right, is same as an equal amount of positive charge moving exactly in the opposite direction. Based on this idea only, the direction of conventional current is defined. So if some negative charge is coming from the negative plate to positive plate, it is equivalent to what? It is equivalent to the positive charge moving from same amount of positive charge moving from the positive side of the terminal to the negative side of the terminal. So the direction of conventional current is taken to be what? It is taken to be starting from the positive terminal of the cell or battery and going and reaching the negative terminal. Clear? And whatever is the value of charge that is moved, it will be same. So we will not consider the movement of electrons anymore. We always will be talking in terms of what? Direction of conventional current. What is direction of conventional current, guys? We will consider that the charges moving are what? Positive charges. And how they are going to be moving? They are going to be moving from the positive or the high potential place to the low potential place. So this is what we will be calling as the direction of conventional current. So after this, right, whenever we talk about any circuit or circuit problems, right, we will be always considering the direction of current to be from where? We will consider the direction of current to be from the positive side of the battery and going and reaching the negative side of the battery. So this is what we will be taking as the direction of the conventional current. Okay, guys, so this is important for us. Next we come to the idea of Ohm's law. So Ohm's law is an important relation that is going to be helping us in all these circuit analysis. We will be using this Ohm's law concept in all the circuit analysis problems. But what is this Ohm's law? If we look at an metallic conductor, what we said, in order to have current we must apply some potential difference. Ohm's law basically states that the potential difference across the conductor, right? So whatever the potential difference that we are applying across the conductor is directly proportional to the current flowing through it at a given temperature. Means, because we have to fix the temperature at a given temperature, whatever the current you see, right, the potential difference you apply is directly proportional to current. Means we can make it into an equation. How? By using a constant. What is the constant we can have? V is equal to I into some R. This R is basically what we are calling as constant. Otherwise what we can say, bring the I to the LHS, what we can say, guys, V by I is equal to constant. This constant is what we will call as the resistance. What is this constant, guys? Resistance. Okay, and resistance is going to be a property of the metallic object. We'll talk about resistance in a little while, but what is it, guys? Resistance is a property of what? It is a property of the metallic object that we are considering. Okay, so whenever we have an object that satisfies this relation, you know what we'll be calling it as? We will be calling it as an ohmic conductor. So whenever we have an object that satisfies the relation, right, we'll call it as ohmic conductor, or we can say ohmic resistor also, both. Okay, so what is Ohm's law, guys? This is something that we already know probably in the lower standards also. In 10th also we probably would have got an idea to it. If we have the current flowing through a conductor, what we see is for the objects, if the potential difference applied is proportional to current, then we can make this into an equation. And the substances or objects that satisfy this, we'll call it as what? We'll call them as ohmic conductors. And here the constant that relates both of them is called as resistance, which will be a property of the metallic object. It will be a property of the metallic object. So resistance, right, its SI unit is ohm, and this is the symbol that we use to indicate. What is the SI unit symbol for ohm, guys? This is the symbol for the ohm. Okay, now we keep telling, guys, whenever we have a new physical quantity, always we must keep an eye on what is the dimensional formula for the physical quantity. Let's say, we got the new dimension, new physical quantity here, which is the resistance. Let's see if we can find the dimensional formula. What we need to find, guys? Dimensional formula for the resistance. Let's see who can find this out. We need to find what, guys? Dimensional formula for resistance. So those who are able to get it right, remember, how do we find the dimensional formula, guys? Using the dimensional analysis. What is the only formula we have? Because what is the dimensional analysis? We must have at least one equation where this quantity appears. So what is the formula or equation we are aware of, guys? V by I is equal to R. Potential difference divided by current is equal to what, guys? R. What is potential difference? Potential difference will be energy by charge. What is potential difference guys? Energy by charge divided by current. So this is how we have to find the dimensional formula for R. So what we are going to do here, energy, what is the dimensional formula for energy guys? mL square T power minus 2. So divide by charge, also will come to the denominator. Charge is what? We will use current as I. So charge will be what guys? What is the dimensional formula for charge? Charge will be equal to I into T, current into time, into there is one more current, I. Clear guys? So what is the final dimensional formula for the resistance? mL square T power minus 3 will come, I power minus 2. So just make a note of it guys. So whenever we are getting a new physical quantity, right, always be open. We can have questions on the dimensional formula. Okay guys? So this is how we are going to find the dimensional formula for the resistance. Clear? Everyone just check it guys. Are you also able to get the same dimensional formula? See, some textbooks write, they can even write it like this: m L square T power minus 3 A power minus 2 they can write, because what they can say is in place of current I, we can also use current dimensional symbol is what? A also can be used as what? Dimensional symbol for current. Okay guys? So this is about the idea of what is the resistance. So resistance of an object, right, is related to the potential difference applied and current by using the Ohm's law. And I've been telling one thing guys, not every object might satisfy the Ohm's law. We'll see the examples also. Not every object might satisfy the Ohm's law. That's why the ones that satisfy the Ohm's law, what do we call them as? We'll call them as ohmic conductors or ohmic resistors. Clear guys? And the other point that we said is this resistance is going to be a property of the metallic object. So what do you mean by the property of the metallic object? This resistance, let's say for example we have the metal object here. This is the cross section area across which we are measuring the flow of current. Okay. Now if we are applying some potential difference V between these two ends, the length of that metal object is what? L. Area of cross section is what? A. What is observed is this resistance is proportional to L by A first, and the constant that we'll get here, it's a proportionality constant. This will be purely a property of the material. It depends upon the property of the material. This is called as so we use a symbol rho to represent it, rho, and this is called as resistivity. What is it called as guys? Resistivity. So resistivity will be a property of the material, means the steel will have some value of resistivity, copper will have some value of resistivity, iron will have some value of resistivity. Like that, every material will be having some value for the resistivity. And L and A are basically the geometric parameters. Even though we have two different objects made up of same iron, if the L and A values are different, right, what is going to be the outcome? The resistance of that object is going to be different. That's why we said what? It depends upon the entire property of the metallic object, means the material properties as well as the geometric properties. Clear guys? Okay. So the resistivity, right, what is this resistivity? It is going to be a property of the material. So we'll learn more about this resistivity as we go along, but this is the factors on which resistance will be depending upon. Okay. Now let's look at what is this resistivity, and one more term we'll be getting to know in this chapter, which is called as conductivity. Now guys, a lot of these terms that you are seeing here, right, will also be able to help you in one more chapter in chemistry called as electrochemistry. So all these terminology which you are learning here, right, you will be using over there also. Not only the terms, the relevant formulae, and also the units, etc. So what is resistivity guys? Just now only we have covered it. What is resistivity? It is a property of the material, we said. And conductivity, it measures how easily a material will be able to allow current through it. So it is basically defined as reciprocal of resistivity. How is conductivity defined as? It is indicated with the symbol sigma. And how are we going to measure it? Sigma will be measured as what? 1 by rho. Okay. And we said whenever we have a new physical quantity, right, we must always be thinking about what? Units and dimensions. Let's see guys quickly if we can tell the units and dimensions. Look at the resistivity. What is the formula we have for the resistivity? R is equal to rho into L by A. R is what? Ohm is equal to what? Rho into length, SI unit is meter, area is what? Meter square. So 1 meter is cancelled. So what we have is the SI unit of rho, resistivity, is going to be what guys? Ohm into meter. And since conductivity sigma, right, is nothing but what? Reciprocal. So sigma unit is going to be what guys? It will be 1 by ohm into meter. We can also write it as what? Ohm power minus 1, meter power minus 1. How we can write it guys? Ohm inverse, meter inverse. This ohm inverse, right, is also written as, just like the way we reverse the letters, right, it's also written as what? Mho. Instead of saying ohm inverse, right, we also accept this one guys, MHO, mho meter inverse. We can also write it as S meter inverse. S represents Siemens. Okay, the SI unit of conductivity, right guys, we can either use ohm inverse, meter inverse, or we can also call it as what? Mho meter inverse, or we can also call it as what guys? Siemens meter inverse. So these are the three representations we can use for the SI unit of the conductivity. And what is the SI unit of resistivity? Ohm into meter. And using the dimensional analysis, we can even find what will be the dimensional formula for both the resistivity as well as conductivity. So what is going to happen if you are able to find the dimensional formula for resistivity? Means conductivity dimensional formula will be what guys? It is going to be just inverse of it. Clear? So this is what we have to look at guys in terms of the resistivity and conductivity. Now as I said, right, all these formulae you will be again looking in the electrochemistry chapter part in chemistry. Okay, so we'll move on to the next idea guys. So what we said, the resistivity will be property of the material. Based on the resistivity values, right, the broad range of resistivity, we'll classify the substance into what? Conductors, which will be having the resistivity values to be very less. So we have a representation of resistivity values at the reference temperature 0 degree centigrade. If the resistivity values is very high, then we'll be calling the substance as what? Insulators, like water, hard rubber, NaCl also. NaCl is ionic substance. In solution it will conduct because of the ions movement, but in the solid state NaCl is what? It is an insulator. Quartz. So all these are what? Insulators. They have very high value for the resistivity. We can see it is in what range? It's in the typically 10 power 5 to 10 power 16. And if you look at the metals, whether it is a silver or copper or aluminum, right, I mean we don't need to remember these values exactly guys, no need to bother about remember the values, just to give you an idea. So the resistivity values will be very low for the conductors, very high for the insulators. And what about the semiconductors? Like if you talk about the silicon or germanium, their values will be intermediate. So the values of resistivity for the semiconducting materials will be what? It will be intermediate between these two extremes. Clear guys? So on what basis, if somebody is asking, right, on what basis we will classify the substance into conductors, insulators and semiconductors? It is based upon the broad range of the resistivity values. Clear guys? So we'll move on to another problem. Let's look at this question guys. Again, I'll read the question, I'll wait for some time. If you are able to get the answer, means you can type it over here in the chat box. Okay, I'll be able to check the answers. Look at this question guys. A wire 250 centimeter length. What is the length of the wire guys? 250 centimeters. And 1 millimeter square cross section area. What is the cross section area guys? So they are giving the length of the wire, they are giving the cross section area. Length is what? 250 centimeter. Area is what? 1 millimeter square. Carries a current of 4 amperes. What is the current that is carrying guys? It is carrying a current of how much? 4 amperes. When connected to a 2 volt battery. It is carrying a current of 4 amperes when it is connected to what guys? 2 volts battery. what is the resistivity of the wire? Means we need to find what? Rho value. What do we need to find, guys? We need to find the rho value. Let's see who can get the answer for this, guys. So what is the formula we have for getting the rho value, right? We know only one formula. What is the formula we know, guys? R is equal to rho into L by A. Now L is known to us. Of course, we have to change the units into SI system. A is also known. We can change that also. Then R must be known. They didn't give us the R value, right? How do we know the R value? They have given us the current and voltage. Then we can find the R value. R will be equal to what, guys? V by I. So from V by I formula, we will get the R value. Substitute the R value here, we will get the rho. Let's see, guys, who can get the answer for this question. As and when you get the answer right, you can just type it over in the chat box. Yes, guys, anyone is able to get the answer? First, what is the R value, guys? Look at this. Voltage is what? 2 volts, right? And current is what? 4 amperes. Means resistance is what? 2 volt by 4 amperes, which is what? 1 by 2 ohm. Okay, so let's get the resistance. Then we have to put this value. R is equal to what? 1 by 2 into rho into L is 250 centimeter. In terms of meter, how much it is going to be, guys? 2.5 meters. Okay. Divide by what is the area of cross section? 1 millimeter square. What is 1 millimeter square, guys? 1 millimeter square will be equal to what? 10 power minus 6 meter square. Because what is a millimeter? Millimeter is what, guys? 10 power minus 3 meters. Okay. So look at this, guys. What is it? 10 power minus 6 will come. So we are looking for the rho, means we have to take the other terms to the LHS. So 10 power minus 6 will go to the numerator. 2.5 will come to the denominator. What is the answer, guys? Rho will be equal to 1 by 2 into 2.5 into 10 power minus 6. So what is 2 into 2.5, guys? 5. What is 1 by 5? 0.2 into 10 power minus 6. What is the SI unit of, because everything we have taken SI unit, right, guys? What is the SI unit of resistivity? Ohm into meter. What is the answer for this question, guys? Okay, what is the answer? 0.2 into 10 power minus 6 ohm into meter. Clear? I think some of us are able to get the answer. Check it, guys. So these are kind of straightforward questions, formula based questions. So if you are looking for exams like NEET and all that, right, we will get only these kind of questions. Clear, guys? So this is how we will be having problems on the resistivity. Okay, so we'll move on to the next idea, guys. So in the discussion about the Ohm's law, right, what we said at a given temperature. So what we said, at a given temperature, the value of V by I will be a constant. Means what? That resistance, which is the constant we talked about in the Ohm's law, is going to be depending upon what, guys? Temperature. And how it is going to depend upon temperature, we will be looking at in terms of what we call as the temperature coefficient of resistance. I mean, we can also call it as temperature coefficient of resistivity. So either we will understand this in terms of what, guys? Temperature coefficient of resistance or temperature coefficient of resistivity. See, broadly, if you look at the metals, I mean, we'll talk about the difference between metals and semiconductors when we go to the micro analysis of the substances. But if you look at metals, right, the conductivity of the metals will be decreasing as we increase the temperature. Means what is going to happen, guys? Temperature increase means what? Sigma is going to be decreasing. And sigma decreasing means what? Rho will be increasing. So the resistivity will be increasing with rise in temperature. This is what we'll observe in the case of what? The metals. And we see a different trend in case of semiconductors. So we'll be learning about it when we go to the micro behavior of the metals and semiconductors. But here when we talk about the metals, right, and also we will know the reason why in case of, maybe you can just make a mark of it here. We will talk about this. We'll give the reason when we are going to understand about the micro behavior of the substances. So for the metals, right, what is going to happen, guys? The conductivity will be decreasing if we raise the temperature. Conductivity decreasing means what? Resistivity is going to be increasing. Clear? Now, how do we understand the dependency of the resistivity or resistance on temperature? We said we will understand this by using what we call as temperature coefficient. Like they were in +1, right? We learn about the coefficient of linear expansion, coefficient of area expansion, coefficient of volume expansion. What is the thing that we have learned there in +1? If we increase temperature means how the length is going to change. If it is increase the temperature means how the area is going to change and how the volume is going to change. We are going to have just a similar relation over here also. So if we take rho naught as the resistivity at some reference temperature T naught, and rho T represents the resistivity at the temperature T. Then if we have small temperature variations, why are we saying small temperature variations is for the large temperature variations, right? This kind of a linear relation. What is the relation we are calling it as, guys? Linear relation will not be satisfied. This kind of linear formula will not be satisfied if you are having large temperature variations. But for small temperature variations, what we have is, remember, this is the kind of formula we have seen in +1 also. For, like remember, for the final length, what is the formula? L is equal to L naught into 1 plus alpha delta T. For the final area, what is the formula we saw? A is equal to A naught into 1 plus beta T. Alpha is what? Coefficient of linear expansion. Beta is what? Coefficient of surface or area expansion. Then we have V is equal to V naught into 1 plus gamma delta T. Gamma is called as what? Coefficient of volume expansion. Okay. So same way we will be having what? Rho at the temperature T is equal to what? Rho naught into 1 plus alpha delta T. So this T minus T naught will be what, guys? Delta T. So this relation is what we will be calling as the temperature variation of resistivity, and we can write a similar formula for the resistance also. How the formula is going to look like? If we talk about just the resistance part, right, R at the temperature T will be equal to what? R naught into 1 plus alpha delta T. So here we'll call alpha as what? Temperature coefficient of resistivity. There we'll call alpha as what? Temperature coefficient of resistance. And we'll see that just like in the case of the alpha, beta, gamma, I mean, don't confuse between this alpha and this alpha. Generally we are using the symbol alpha. Okay. The units of all these temperature coefficients, right, will be simply what? Degree centigrade inverse or Kelvin inverse. What will be the units of all these temperature coefficients, guys? It will be temperature inverse. That will be the unit of all these temperature coefficients. Clear, guys? So how we are going to study the dependency of the resistance or resistivity on temperature? We will study this by using the temperature coefficient of resistance or temperature coefficient of resistivity. And we don't need to think of it like a new concept. It is something that we are already familiar with. How we will understand the variation of length with respect to temperature, how we will understand the variation of area with respect to temperature, how we will understand the variation of volume with respect to temperature. Similarly, here we are talking about what? How we will see the variation of resistivity or resistance. Remember these formulae, guys, because we can have questions based upon this formula. In fact, in some of the previous years, right, in JEE as well as NEET also, we got questions on this temperature coefficient concept. Okay. So if you look at the idea of metals, that's what we said. For metals, what we said is the resistivity value is going to increase. So as we increase the temperature means what is happening, guys? The resistivity value is going to decrease. Sigma will be, decreasing, and rho will be what? Increasing. So this is for the metals. In case of the semiconductors, so this last graph we are seeing is what, guys? Semiconductors. Like we talk about a silicon or a germanium. What we'll observe in the case of semiconductors is the rho value, if you increase temperature means rho value is going to decrease. So increasing temperature will decrease the resistivity. So not every object will have rho increasing along with temperature. That happens only for what? Metals. On the other side we have materials like nichrome and some alloys. For them, right, the rho value will not see much change. It will not have much change with respect to temperature. So we'll always, though it is looking like a straight line kind of a thing here, it will be almost like we see the difference, right? How much it is changing? 1.1 to 1.2 for a temperature variation of how much? Nearly 200 to 800 Kelvin. So this much temperature change, we are not seeing much jump in terms of the resistivity value. So we have broadly the metals, right? Increase in temperature means what? Rho is going to increase. Semiconductors, increasing temperature means what? Rho is going to decrease. And we also have substances like some alloys where the rho value will not change much with respect to temperature. Clear, guys? So by that logic, right, if you look at the formula, rho t is equal to rho naught into 1 plus alpha delta t formula, right? For these metals, right, this alpha is going to be what? Positive, because the rho t will be increasing with increasing temperature. The alpha will be negative for the semiconductors, and alpha is almost 0 for these alloys where we don't see much change of resistivity with respect to temperature, like nichrome or some of the alloys that we talked about, right? So for them the alpha value will be almost equal to what? 0. So this is about the concept of temperature coefficient of resistance or resistivity. Clear, guys? So if you are clear with this idea, means we can go to the questions. Okay, look at this question, guys. Take some time to solve the question. There is no hurry. So look at this question. A coil wire has a resistance of 25.00 ohms because they are giving up to 2 decimal places. What is the resistance at 20 degrees centigrade, guys? 25.00 ohms. And a resistance of 25.17 ohm at 35 degrees centigrade. At 20 degrees centigrade, what is the resistance value, guys? 25. 35, what is the resistance value? 25.17. What is its temperature coefficient of resistance? We need to find what, guys? We need to find the alpha value. We need to find what, guys? We need to find the alpha value. So what is the formula we have? R at the temperature T is equal to what, guys? R naught into 1 plus alpha delta T. Okay, so we can also write it like this. Check it. R naught plus R naught alpha delta T. Basically we are opening up the bracket and then distributive law we are using. So if we take it to the LHS, means RT minus R naught will be equal to what? R naught into alpha delta T. We are looking for alpha, right? Means what is alpha value going to be, guys? Alpha will be equal to what? RT minus R naught by R naught delta T. So this is the formula. We can probably, we don't need to remember the formula because we are just using the base relation. Clear, guys? So using this we have to get, so RT means what? We will take 35 as the temperature T. R naught will take it as what? The resistance value at the 20 degrees centigrade. Clear, guys? So here delta T will be equal to what? The final temperature is 35 minus initial temperature was 20. Delta T will be what, guys? 15 degrees centigrade. Okay, so look at this, guys. Anyone is able to get the answer for this? RT value is what? 25.17. 25.17 minus 25, that is the numerator part, divided by 25 into delta T will be what, guys? 15. So numerator is what? 0.17 by this 25 into 15. Okay, so just do the math, guys. And what will be the unit, guys? Degree centigrade inverse. What is the unit of alpha going to be? Degree centigrade inverse. Anyone is able to get the answer for this, guys, approximately? What is the answer for this? We have to just do this math. 0.17 by 25 into 15. Check it, guys. What will be the approximate answer for this? Yes, anyone was able to get the answer? Okay, so look at this guys, we must be getting it as what? 4.5 into 10 power minus 4. What must be the answer guys? 4.5 in 10 power minus 4. If you do the simplification, right, it will be coming like what? Some 4.49 something into 10 power minus 4 will come. It will be what guys? 4.5 into 10 power minus 4. And what will be the unit of alpha? It will be what? Degree centigrade inverse. Check it guys. So what are we doing in this question? Basically they are giving two temperatures. First temperature is what? 20. Second temperature is what guys? 35. And they are giving the resistance value at 20, resistance value at 35. And they are asking us what? The alpha value. So what we are doing basically is we are taking R0 to be what? 25, which is the resistance at the base temperature. R0 is what guys? Always base temperature. Base temperature we are taking it as what? 20 degrees centigrade. Okay. So the base temperature is taken as what guys? 20 degrees centigrade. R0 value. Then what is the formula we are having? RT is equal to R0 into 1 plus alpha delta T. And rearranging from this formula, right, we are getting alpha value. What is the alpha formula guys? RT minus R0 by R0 into delta T. That is the formula. So RT means what? 25.17. That is the second temperature. Minus R0 is what? 25. Divide by R0 is what? 25 into delta T. Delta T means what? The T minus T0, right? That is delta T. T is what? 35. Minus T0 is what? 20. So which is what guys? 15 degrees centigrade. That's why the alpha value is coming in what? Degree centigrade inverse. Clear guys? Okay. So just check. Most of us must have got the answer for this question guys. Okay. So this temperature coefficient of resistance or resistivity is an important idea. So we have to be careful about this. So with this we'll go to the next question guys. Let's see if we can get the answer for this. There is another question based on the temperature quotient. The resistance of the platinum wire. What is the question guys? I am reading out the question. The resistance of the platinum wire of a platinum resistance thermometer at the ice point. Ice point means what guys? The temperature where the ice will be formed, which is what? 0 degree centigrade. What is the resistance at the ice point guys? 5 ohms. And at steam point means what guys? 100 degree centigrade. Steam point, what is the resistance value? 5.23 ohms. When the thermometer is inserted into a hot bath, the resistance of the platinum wire is coming as what? 5.795 ohms. When it is inserted into a hot bath, right, the resistance is coming as what guys? 5.795 ohms. We need to calculate the temperature of the bath. What we need to find guys? We need to calculate the temperature of the bath. Okay, let's look at this question guys. Here the 0 degrees we'll take it as what? The base temperature, where we'll have the R0. Okay, at 100 degrees centigrade, which is the steam point, we will call it as what? Let's say for example R100. Then at the temperature T, which you have to measure, the resistance is given as what guys? 5.795. At the temperature T, where we have to measure the value, the resistance is given as what guys? 5.795. So how are we going to find the temperature T value? So if you look at this, all of them are related to what? Alpha. All of them are related to what guys? Alpha. In the previous problem only we saw. What is the formula for alpha guys? RT minus R0 by R0 into delta T. This is the formula we have, right? That is the alpha formula. What is the alpha formula? RT minus R0 by R0 into delta T. So we are going to use this alpha formula first between the base temperature and 100. Second, between the base temperature and the unknown temperature. Clear guys? We are going to use the alpha formula in two cases. What are the two cases? First is what? Between 0 and 100. Second is between 0 and the unknown temperature. So first, when we use it between 0 and 100, what you are going to get guys? Look at this. R100 minus R0 by R0 into, what is the temperature difference here? Between 0 to 100 means what is the temperature difference guys? 100 is going to come. Okay. Then next time when I write the alpha formula by using base temperature and the unknown temperature T, what will be the formula? RT minus R0 by R0 into, here the temperature difference is what? Base temperature is 0. This temperature T means what is the temperature difference, guys? T will be the temperature difference. This T is what we are supposed to find. In both the case, alpha must be same, right? Means what we are going to have? R100. So now I am going to use these values itself. Look at this, guys. R100 is what? 5.23. So 5.23 minus 5 means what? 0.23. Look at this, guys. 0.23 by R0 is what? 5 into 100 is equal to RT minus R0 means what? 5.795 minus 5, which is what? 0.795. 0.795 by R0 is what? 5 into T. 5 is cancelled. We read T value. So T will be equal to what, guys? 0.795 into 100. Cross multiply we have to do. 0.795 into 100 by 0.23. 0.795 into 100 by 0.23, which is what? 79.5 by 0.23. What is it, guys? 79.5 divided by 0.23. Check it, guys. What will be the approximate value for this? How much will be the approximate value for the T? Because we are supposed to find what? The temperature T of the hot bath. We are supposed to find the temperature T of the hot bath, right? So understand, guys, what we are doing here. We are having the base temperature, steam point, and then unknown temperature. We are going for the alpha formula between the base temperature and steam point. Previously only we saw that alpha formula. What is it? Between the reference and any temperature T. What is the formula for alpha, guys? RT minus R0 by R0 into delta T. Correct. So here when we write the formula means R100 minus R0 by R0 into, here the temperature difference is what? Between 0 to 100, 100 will come. Second time we are writing alpha formula by using what? The base temperature and the unknown temperature T. Here what is the formula, guys? RT minus R0 by R0 into temperature difference will be what? T minus 0 means T will come. This T is what you are trying to find. From both these alpha values must be same, right? We equate both of them. So R100 is what? 5.23 minus 5, 0.23. Divided by R0 is what? 5 into 100 is equal to what? 5.795 minus 5. RT minus R0. 0.795. Divided by R0 is 5 into temperature difference is what? T. Cross multiply, we will get the value of the temperature. It's what, guys? Temperature must be coming as what? 79.5 by 0.23. Approximately how much is the answer, guys? Just check it. It must be coming as what? 345. Approximately it must be coming as what, guys? 345 in terms of the degree centigrade. Because the value of temperature is taken in what, guys? Degree centigrade. Clear, guys? So just check the simplification. And these problems, right, sometimes, we will have to do the simplification also. It's not like, every time we'll have very easy and cancellation straight away coming like that. We may not have. In some problems, if you are lucky and maybe in especially mostly NEET, we'll have these easy cancellations going. But even in the board exams and the other exams like JEE or something, we'll have the calculation part involved. Okay, guys? Check this. All of us are able to get this, guys? Okay. So if you understood these two questions means broadly you must be comfortable in terms of the idea of this temperature coefficient of resistance and then resistivity. Okay. So we'll wait for the others also to get these answers. See, the thing that we need to be very clear is like, most of the problems that we're trying to do, right, guys, as we go through the session, make sure that you try and work it out during the time that is given. Because if we are giving a gap of, say, for example, 1 minute, right, probably the question itself might be a 1 minute kind of question. And even if some of the questions you are not able to give in the stipulated time, right, make sure that even, because you might note down the problem statement, right, even after the session is over, you can just work it out. Okay. So we'll move on to the next concept, guys. So these are the kind of questions that we can expect on the temperature quotient of resistance or resistivity. Now when we talked about the Ohm's law, right, what we said, not every substance might follow this relation. What is the relation? V by I is equal to R, or V is equal to IR. Because if you look at a given temperature, right, R is constant. R is changing only when you change temperature. Means V and I, if you look at the graph, it must be coming like what? It must be coming like, if you plot the V and I graph, it must be coming like what? Straight line. At a fixed temperature, because it is like what? Y is equal to M into X. No, it will be coming as what? Straight line. So that is what is expected out of the substances that exactly follow the Ohm's law. Metals, right, will broadly satisfy this relation for certain temperature. I mean, for certain range. If we increase the voltage very high, means we'll see some deviation. Like, we'll see the curve changing from the straight line kind of a relation. We'll see that it will be changing into a curve, but not in the small voltage range, but very high voltage range. But there are some substances which totally behave differently, and we'll study about this class of devices, which we call them as diodes. So diodes, we will be learning about it in the chapter of semiconductors. So diodes are made by using what? Semiconductors. There are two interesting things about the diode. If you see the graph, right, so never the graph is straight line. It is always what? Curved. Means the voltage you apply and the current, they are not having a linear relation. So there is no linear relation at all. That's one point. The other difference is, if you look at the normal metallic objects, like say for example, you have a metal object. Now whether we apply a potential difference with this is positive, this is negative, what we see, current is going to flow like this. Other thing is, I can apply positive potential here and negative potential here. This is another way I can apply. So I can either apply the left hand side of the object as positive and right hand side negative. That is one way. Or I can make the right hand side positive, left hand side negative. The normal metals, right, in both the cases, they are going to give us the same value of current. In terms of value, the current value is going to be what? Same. So whether you apply the potential towards right side to left side or left side to right side, potential difference, because we are changing what? The direction of the potential difference. We are going to be getting the same value of current. Current is not going to change. The direction of current will change, but the value of current will not change. But these diodes, right, we will learn about it. If you apply the potential in the reverse direction, like here you can observe one thing. If you apply the potential in one direction, basically we will be calling it as forward biased. So we'll learn about this in the semiconductor chapter, but here just some basic understanding. In forward bias case, right, we'll see the current is in which range? Milliamperes range. What is the range of current? Milliamperes. If you apply the potential in the reverse direction, like the other side, then we see the current is in what? Microamperes range. So this is what we will be calling as reverse biased. So the normal metal objects, right, what they are going to do, whether you apply the current potential difference this way to that side or that way to this side, the current numerical value is going to be the same. And they will also satisfy what? The straight line kind of relation between voltage and current. But the diodes, they show a different behavior. First, they will not show any linear relation. That is one. Second thing is what? They will change the range of current from what? Milliamperes to microamperes when we reverse the direction of voltage drop. So one side we will call it as forward biased, where the current is a little bit higher. It will be in the range of milliamperes. Reverse bias means the current will come down to what? Almost like microamperes kind of a range. Clear, guys? I mean, I'm not expecting you to understand this concept here, because why the diodes are behaving like this, we will understand only when we know about what is a diode, how a diode is made up and all that. Here it will be more like an information for us that okay, it is not like every substance has to behave as per the Ohm's law, but we have examples which don't follow the Ohm's law. Clear, guys? And even some substances like gallium arsenide, what we see is there is going to be a complete non-linear relation. Means for some time we'll see that we'll have the current will be increasing with increasing voltage, like almost like a straight, and then we'll see saturation, and then we'll see even regions where there is a negative Like if you look at further increase of voltage, what is happening? The current is decreasing. So this region is called as what, guys? Negative resistance region. What is it called? The negative resistance region. And this behavior, right, will mainly come because of the crystal defects. So in chemistry solid state you will be learning about this. So why these non-linear behavior and negative resistance behavior comes? Because of the crystal defects and the lattice aspects of these substances like gallium arsenide. Okay, so the idea is like this, guys. Not every substance might follow the Ohm's law. We have examples of substances that will not be following the Ohm's law. What is one example? This one, the example of the diodes we'll study in very much detail, because semiconductor chapter, right, we are going to be looking broadly about the idea of diodes. Okay, and we'll also have substances that will show general non-linear behavior, like the case of these gallium arsenide kind of complexes. Okay, so this is about the idea of the non-ohmic behavior. Okay, guys. Now in every session, right, what we thought we'll be doing is we'll look at some questions, some miscellaneous kind of questions that we will go through. They will cover most of the concept that we have dealt in the particular session. Like here today's session, right, we have some miscellaneous questions. Maybe these questions you can think of it like probably NEET level questions or JEE level questions. Okay, so look at these questions, guys. We have a set of questions, like we have 3 questions based on whatever we have covered in this particular session. And this concept, right, especially the problem 7 we are seeing here, this concept we'll be using it in other chapters also, like moving charges, even the moving charge chapter and EMI also we will use this concept. Look at this question, guys. In the Bohr model, electron of hydrogen atom moves in a circular orbit of radius how much? 5.3 into 10 power minus 11 meter. What is the radius of the circular orbit given to us, guys? 5.3 into 10 power minus 11 meters with a speed of 2.2 into 10 power 6 meter per second. What is the speed of the electron given to us, guys? 2.2 in 10 power 6 meters per second. Okay, now this is the question. Determine the current I in the orbit. What do we need to find, guys? We need to find what is the current I in the orbit. Check this question, guys. I'll tell why this question is important, because in the moving charges and magnetism chapter also we are going to be discussing about this electron orbit. What do we call this, guys? Electron orbit. So if you look at electron orbit, right, you mark any point in that orbit, the electron is going to be repeatedly crossing that point. So I'll just give you the idea, guys. You can work out the question. The electron is going to be repeatedly crossing the point. How many times in a second? How many times the electron is going to cross? As many times as that of the frequency. What is F, guys? F represents what? Frequency. And what is frequency formula? 1 by time period. What is time period formula? If you have the circumference or the perimeter of that orbit is 2 pi r divided by v, speed, it gives us what? Time period. Means frequency will be what, guys? 1 by time period means what is the formula? V by 2 pi r. Frequency will be what? V by 2 pi r. Okay, so the electron is passing through that point. How many times in a second? F number of times. So F is basically the frequency, that many number of times. Say for example, if the frequency is, I'm just telling you the number, frequency 10 means 10, it means what? In a second it is crossing how many times? 10 times it is crossing. Means how much charge would be going through this point in 1 second? In 1 second, how much charge will be going through the point, guys? E is the charge of the electron. This much charge, how many times it is crossing per second? F number of times. So this is basically the current. So if you have any electron orbit, right, guys, what is the current value in that orbit? Just make a note of this formula. What is the current value of that orbit, guys? I will be equal to what? E into F. E is what? The charge of the electron. F is what? Frequency. And what is the frequency formula, guys? What is the frequency formula? Frequency will be what? V by 2 pi r. So this formula, right, we will use again in the moving charge magnetism chapter as well as the electromagnetic induction chapter also. We'll use it. So this is the formula for finding the current in the electron orbit. What is it, guys? This is the formula for finding current in the electron orbit. Now E value we know. What is the E value? Basic charge. What is it? 1.6 in 10 power minus 19 coulombs. V is given to us. Speed they have given to us 2.2 in 10 power 6 meter per second. Radius is also given to us 5.3 in 10 power minus 11 meters. Just substitute and check the answer, guys. What will be the current? We need to find what is the current in the orbit. Check it, guys. What is the current value? We need to find what is the current value in the electron orbit. So remember, guys, what is the formula for current in the electron orbit? EV by 2 pi r. E is what? Electron charge. V is the speed of the electron in the orbit, and r is what? Radius of the orbit. Yes, guys, any answers? So it's like a formula question. We just need to understand the idea here. What is the idea here, guys? If you look at electron orbit, any point you mark, the electron is going to cross the point in a second. How many times? F number of times. F is going to be what, guys? Frequency. What is F represents? Frequency. And what is the frequency formula? 1 by time period. What is the time period formula? 2 pi r by V. So which means frequency will be what, guys? V by 2 pi r. What is the frequency formula? V by 2 pi r. So current is going to be what? Charge value multiplied by how many times it is crossing through that point per second. E into F. So E into V by 2 pi r. That is the current. Okay. So look at this, guys. Anyone is able to get the answer? Check it, guys. The answer must be coming as 1.06 milliamperes. I am not solving the detailed question because I gave you the idea. What is the answer must be coming as, guys? It must be coming as what? 1.06 milliamperes. Okay. Maybe, you can just check this answer, guys, one more time. Okay, so at home, once we finish the session, right, we'll wind up the session by 7:30. So once we finish the session, you'll be able to again go and check those who are not able to get the answer. Okay, so we'll go to the next question, guys. There's another miscellaneous kind of question. Look at this question, guys. The current in a wire varies with time. The current in a wire varies with time according to the equation. This is the equation. I is equal to 4 plus 2t. What is the equation for the current, guys? I is equal to what? 4 plus 2t. This is the equation for the current, where I is in amperes and t is in seconds. I is in what, guys? Amperes, and t is in what? Seconds. The quantity of charge which has passed through the cross section of the wire during the time t is equal to 2 seconds to t is equal to 6 seconds. So we need to find how much charge is flowing through that particular cross section of the wire from how much time, guys? 2 seconds to 6 seconds. Why I said this is a miscellaneous question, right? Here current is what? Variable current. Like the way in mechanics we'll have what? The speed is variable. Remember, guys, what is the instantaneous value for the current? dq by dt, right? What is the instantaneous value for the current? dq by dt. From here, guys, this problem we can solve only by using what? Integration method. From here, I dt will be equal to what? dq. This is a basic integration, guys. I dt is equal to what? dq. We have to integrate the LHS part. LHS is by using what? Time. Time is what, guys? 2 seconds to 6 seconds. I dt, I means what? 4 plus 2t dt is equal to LHS is what? Integral 0 to q dq. This is the q value. Now we have to do this integration, guys. Integral 2 to 6, 4 plus 2t dt. Okay, so we'll split this, guys. We'll split it, which is basically what? Integral 2 to 6, 4 dt plus integral 2 to 6, 2t dt. Okay, so we'll have to conclude this. What is 4 dt means? Integration of 4 is a constant, comes out. Integral dt is what, guys? T means 4 into 6 minus 2 will come, plus integral 2t dt will be what? T square. What is integral 2t dt, guys? It will be t square, means 6 square minus 2 square will come. Yes, guys, any answers? So this 6 minus 2 is what? 4. 4 4s are what? 16 plus 6 square is what? 36 minus 4, which is what? 32. What is the answer, guys? What is the answer coming as? 48 coulombs. Check it, guys. Here we are using what? The idea of integration method. Why are we using the integration method? Because it is a variable current. So at an instant of time, we see the current formula is what? 4 plus 2t. So I is equal to dq by dt. Means dq is equal to what? I dt. We want to find the total charge flowing, means we have to integrate this I dt term from where to where? Initial limit 2 seconds to final limit 6 seconds. Here we are using the basic integration techniques. What are the basic integration techniques, guys? Integral dx means what? X. We have to substitute the limit. Final limit value minus initial limit value. Integral 2x dx means what, guys? X square. This basic integration we need to remember. Okay, guys. Check this question also once we finish the session. So what is the answer for this question, guys? 48 coulombs must come. These kind of basic integration questions, right, we would have done in the +1 mechanics also. Okay, look at this question, guys. These kind of questions, right, they come repeatedly in the NEET kind of examination. Look at this. A copper wire of resistance 4 ohms. What is it, guys? A copper wire of resistance, how much? 4 ohms is melted and redrawn to thrice its original length. It is basically melted. We are melting the copper wire and we are drawing it to what, guys? 3 times of the original length. We are making it to what? 3 times of the original length. Find the resistance of the stretched wire. What do we need to find, guys? We need to find the resistance of the stretched wire. Think about it, guys. We have a normal wire, let's say for example, of some length L and the area of cross section A. For this, what is the resistance, guys? R is given to us. What is the R value? 4 ohms. Okay, let's keep it. Now we are melting it and making it into thrice the length. Guys, we must understand one thing. When we stretch it to 3L, right? See, volume must be constant, right? Because we are not creating the material as such. We are just melting the copper and then making it to what? 3 times the length. So initial volume is what? A into L. Let us say final area is what? A dash. Will be equal to A dash into 3L. Means what is the A dash value, guys? A by 3. So the final area is going to become what? 1/3 of the original area. So if you make the length to be what? If you make the length to be what, guys? 3L. The area is going to become what, guys? Area is going to be becoming what? 1/3. Look at it. Why it is going to become 1/3? Because the volume must be what? Constant. The initial volume A into L will be equal to what? The final volume. What is the final volume, guys? A dash into final length is what? 3L. So from here what we are getting? A dash is equal to what? A by 3. What is A? Original length. Okay. Now initial resistance is 4 ohms. Means what? 4 is equal to rho into L by A. That's it, right? Resistance value is equal to what? Rho into L by A. Now we need to find the new resistance. What is the new resistance? R dash formula. Same material, right? Rho will be not changing. Into what is the new length here, guys? 3L. Divided by what is the new area here? A by 3. Means we can see it is going to be what? 9 times of rho L by A. What is rho L by A, guys? 4. 9 times of rho L by A means what? 9 into 4, how much it is, guys? 36 ohms. So if we have the same copper wire, we melt it and make this into 3 times the length. Then what is going to be the other effect of it? The area is going to become what? 1/3. The area is going to become what, guys? 1/3 of it. If the area is becoming 1/3, right, then it is going to change the resistance. How it is going to change the resistance? New resistance R dash will be equal to what, guys? Rho into 3L by, which is the new length, divided by new area is what? A by 3. Means the 3 will go to the numerator. 3 3s are, it becomes what? 9. So what is the new resistance R dash, guys? 9 into rho L by A. Means rho L by A is already what? 4, which is the given. So which means what? 9 4s are 36. Clear, guys? So this is about the approach of solving these kind of questions. Okay, so this is what we wanted to broadly cover in this session, guys. And in the next session, right, we'll continue with some more things left on the idea of the resistors, and then we'll get into the circuit problems. Okay, so just whatever the things that we covered in this session, right guys, make sure that you go through the problems, particularly whatever the leftover problems. If in case you are not able to get the final answers right, just make sure that you check back on the final answers. And the next session we'll be having it on Monday. So I guess the sessions will be from where it will be from Monday to Saturday. Every day we'll have it from 6 to 7:30. Okay, it's like a 1.5 hour session. And this weekend time, right, you can go back and check some of the things in the electrostatics also, so that whatever the ideas that we'll use in electrostatics, right, you will be able to correlate them easily. Okay guys, so we'll see again on Monday same time around 6 o'clock, and